So if we were to take a look at 4, reminds me, we did get some answers, right? All right, so the farthest we could was what, 286 or 2? Sorry, you're right. And the shortest was what? And then maybe we didn't do this, the best overestimate for the whole entire trip. Oh, you guys did that for homework, didn't you?
We did it in class first.
Okay. All right. So 298 feet. And the best underestimate, 122 feet. So if we wanted to find the greatest possible error, well, what we mean by the greatest possible error is the difference between our over and under estimates. So it looks to me like, what's that? 176 feet. Now, if you wanted to have your error, right? If you wanted half the amount of error, you would take your over and under and average them. But in this case, if you went with 298, you could be off by 176. If you went with 122, you could be off by 176. And there are actually whole courses devoted to error analysis. Like if you're going to be an engineer, you know what you do always is going to be within a tolerance, right? You know that like the beam that you manufacture and the bolts that you manufacture are never going to be exactly mathematically perfect, but you know they're going to be within a certain tolerance. And that error is really important because you have to understand how that error is going to affect whether the bridge is going to collapse or not, right? You have a bunch of errors based on like the bolts, the steel beams, the concrete, and that's why you over-engineer something, right? Yeah. Right? Because if you under-engineer it and all those errors add up, you're bummed, right? That's when the bridge collapses. So you could take a whole course in how bad are errors. Okay. Let's see. How should we do this? Okay, so Drew, Ian, Katie, David, Sam, you're one group. And then, actually, can I just do it in... Yeah, I can. All right. Yeah, that's fine. Yeah, you guys are one group, so it's the left side against the right side. I want you to do the next part, H, I, and J. Before you do H, I, and J, though, you have to put in numbers. You have to make up values. It says, in your group, supply values for the velocity, and they need to be consistent with the fact that the car's slowing down. Okay? And actually, I do not want the left half of the room and the right half of the room talking. I would like it very much if you picked different values for the velocities at 1, 3, and 5 seconds. Right? So, it can be anything. Yes, exactly. All right, so pick it and then divide up the work and do H, I, and J, and then we'll talk. I'm giving you like 2 minutes.
Like 60, 20. Okay. But the difference is 45 and 60.
It doesn't matter. The picking's supposed to be the easy part.
Yeah, what are we picking for them? 40?
And then you can divide. Like some people can do the over, some can do the under, and then you can compare.
No, for you and I do the over. Okay. Well, we have really bad communication problems, guys. Seriously. Let's just do it on
Wait, are we supposed to keep going or just make it?
H, I, and J, yeah. So, like, some of you can do the over, some can do the under.
I'm missing one battery. And I don't know.
The over, guys, I know what the over is.
We're doing 6.
Doesn't matter. The delta T is 1.
Well, don't you get the same answer?
Yeah.
Yeah. Mark, I is 88.
Yeah. The difference between H and I. So H is 255. Right? Yeah. And then 167.
All right, I know you guys did it right. So, right half of the room, what was your over?
259.
No.
Right
Oh,
half, 255.
Oh, right.
oh, yeah, you're right, not my right.
Okay.
255, your lower, 167, and so your, oh my gosh, your difference was 88, you said?
Yeah.
Okay. 7. All right. And left half over?
259.
So a different overestimate. Doesn't that sort of make sense if you pick different numbers?
Yeah.
Lower?
171.
A different under. That makes sense. The difference?
88.
88. So even though the numbers are different, the estimates are better. And why are the estimates, not only are they better, they're exactly the same. And why are they better? Yeah. Right? It's a smaller margin, right? We now got within 88 of the right answer. Before we were within 176 of the right answer. It is. But can we talk a little bit about maybe where these came? It's not a total coincidence. Actually, 176, if you think about it, what was delta t up here? 2, and down here delta t was 1. And if you look at the difference between your f of b and your f of a, if you look at your y values, 88 times 2 is 176. 88 minus 0, or 88 times 1 is 88. If we were to measure it every half second, it'd be 44. Right? So actually there's a very special relationship between how often we measure and the y values and the delta t values. And I'll give you that relationship, but conceptually the important thing is this. The smaller the delta t, the closer your over and under estimates, and the better or more accurate your answer. And this is sort of what Sam was saying at the beginning of class. Like, is it always going to be that way? Yeah, it is. The more we measure, the better it's going to be. So, let's see. The difference between your upper and lower, something happened there, upper and lower. Sometimes we say that that's the same as your maximum error. Oh, gosh, this is bad. Can't spell today. Here's what it's equal to. It's equal to f of, sorry, I need absolute value signs. F of b minus f of a, the difference of the y values, times delta t. So if you look at your endpoints and you subtract 88 from 0 and you take the absolute value, you multiply by delta t, that gives you the most that it's going to be off by. And let's look at it. Your maximum error, if you're multiplying, if delta t is small, what's true about your maximum error? It's going to be small. So the smaller you make delta t, the smaller your error is going to be. And that's pretty consistent with what we conceptually understand. What's the bummer about doing small delta t's? You got to add up so many things. So it would. Let's to also recap for those in the home audience, I guess like Dan and Katie. I did tell you there's a formula to relate delta t and n, the number of intervals, and we said that delta t was equal to b minus a over n, and that was in the reading. But just as a reminder, reminder, n is the number of intervals, and this is like the change in x. Okay. What's going on? You think they're coming to see our class? All right, so if you could pick one administrator to be in the lockdown room with us, who would it be? That was pretty fast. All right, moving on. Yeah, I guess, yeah, he does. All right. All right. I'd like to take a look at, I think, number 6, because I think it ties into the problem that Julia did. We can talk a little bit about left and right, over and under, and this. This question specifically asks for right and left hand sums, and we'll just look at A. We're going to look at x squared plus 5 on the interval 0 to 6. And they tell us what delta x is. So if delta x is 2, just out of curiosity, what's n going to be? Say it loud and proud. 3. Right? If the interval is 6 wide and we're doing delta x of 2, we're going to have 3 intervals. Okay, so let's get a picture. X squared plus... Do you want to do the EDX instead, since we did one like this yesterday, or you don't care? Okay. All right. All right. So I think I'm going to need 0 to 6, and then my y values are going to have to go up to like 40 or something. Right? I think they're going to have to be pretty high. And I'm actually going to turn my grid off. Oh, really? What a bummer. You're right. I'm going to leave it like that for now, but you're right. Okay, so now that I have the graph, let's see.
Could we, like for a pattern like this, could you just do kind of like the Julia one and make a table?
Right, okay. So what I want to do is I want to tie together the table with the graph. Okay, that's what I'd really like to do. And I will go get the table. And let's see, we want to set the table to go up every 2. Is that right? Isn't that what delta t is? Yeah. Okay. So if I do that, I'm going to go, let's see. I'm going to just get this small table. All right, so do you see, if we were doing this first interval, right, from 0 to 2, I could pick 5 or 9. Let's work on doing the left hand first. If I were doing the left hand, would I pick the 5 or the 9? 5. And I want to show you what that looks like on the graph. It looks like this rectangle. This rectangle is 2 wide and 5 tall. What's the area of that rectangle? 10. What were you going to do here? You were going to do 2 times 5, right? For my next interval from 2 to 4, what's the left-hand number that I'm going to pick? 9. That's this rectangle, which is 2 wide, 9 tall, so that's 18. And then finally for my last one from 4 to 6, wait, why does this go so far? Oh, I'm a knucklehead. I apologize. I still have my x scale onto halves. So actually 0 to 2 is this. Remember yesterday I set my scale to 0.5? So this is actually 2, and then this is 9. And then the last one from 6 to 8, no, 4 to 6. What happened there? From 4 to 6, I'm going to pick 21, right? And that's this rectangle. So I want you to think I want you to be able to look at the table and look at the graph and see that there's a connection. And I love the fact that yesterday when we were given an equation, Julia went to the table because that was something comfortable. But I want you to be able to see the connection between the two so you don't always feel like you just need a table. And I want you to think about the left hand in this side. In this one, can you see that the left hand decides how tall the rectangle is? And over here, it's the left hand that decides how tall the rectangle is. And over here, it's the left hand that decides how tall the rectangle is. Is that okay? Do you see how that's the left hand? And I actually would say, can you see immediately whether, in this case, the left is an under or over? Can you all say under? Definitely?
Under.
Like, this is going to be... this is going to be too little. It's going to be our underestimate. Okay? And that should tie together with the fact that when we looked at the table, you were always picking the smaller value, 5, 9, and 21. Is that all right? Okay. We could do the right hand as well. If we were to do the right hand, just as a quick picture, the right hand would look something like this, where all the rectangles would be too big. Okay? All right, so... Awesome class. Very impressed. You asked all the right questions today. So thank you. I would concur. I would say you are amazing. Yes, you are amazing. You can hear that over and over again. Have an awesome weekend. Good luck with basketball. Have a great weekend. That's not too bad. 2-day week of real classes. Enjoy your day. Have a great Friday.
Yes. I also brought.
Oh.
What?
Are you just like holding on to Katie for like your life?
Yeah.
Have an awesome Friday. Have a good weekend.
Wait, can I take a look at my exam, 8th period? Since I wasn't here yesterday.
Can we find another time other than 8? 8's not great for me today, and I'd like to be. Any like lunch, free periods, anything else? I'll be here. Awesome. Thank you, David.
Oh, same thing with physics?
Yep, I think I actually have both exams up here, so I can show you both at the same time.
Class. I'm in a bad mood.
Why?
Just so you know,
Exact reason.
there were all these administrators that walked up, and
Big time.
they're like lockdown, and I was like, all right, if we had a lockdown, which administrator would you like to be locked down with? And immediately they said, Mr. Schofield. But then David Bellier said, wait, does Mr. Nelson count? Oh, Mr. Nelson, definitely Mr. Nelson. That's how I turned when they realized that they could pick you.
But,
Nice computer. What was I going to say? Oh, yeah. You?
Oh, you were... Sorry,
Yeah.
I thought you were implying that I acted like I was bored.
Up here and get her little notes because
To work on that.
things
Okay.
she's seen
Like,
me
I
do
got
the
it
past
to work.
week.
I don't want to.
I wish you were there.
I didn't do it to work.
I thought I knew what I
I
did.
actual rules of integration. I used like sleight of hand to get it to work.
You guys need help?
So I'll show you how I did it.
All right.
Like I did this.
Wait, where's the today?
Oh, but that's clever.
Right. And so then I was like, it's that, and it's this, so it's one, and it's a new substitution problem.
What's wrong with that?
No, there's nothing wrong with that.
That's great.
But the kids were like, you just gotta figure out a better way to do it. And I was like, I don't.
I highly doubt it. I mean, I'll look, but like, did you ask Pat too?
I didn't. I figured one of the two of you might. Like, it's not an integration by parts problem, or at least not that I can figure out. I mean, it could very well be an integration by parts problem. I can't.
It's not how I saw it. Got it. Thanks. All right.